Hi everybody, welcome back. Today we're going to be looking at how derivatives affect the shape of a graph. Now, on the screen here you have the graph of a function. And the function here is outlined in the color blue. And I've then went ahead and denoted a few x-coordinates for this function where certain values are going to occur that we want to pay attention to. Okay, so one of the first things that I want to start analyzing here is when my derivative of my function is going to be positive. Now remember, when we're talking about the derivative of a function, we're really talking about the slope of the function at a given point. And you're going to notice that all of these derivatives that I am plotting here, or that I'm graphing here, all of these derivatives are positive for this function. Now, this will then tell us, by observation, that as long as my derivative is positive, then my overall function is going to be increasing. So that's one of the things that we definitely get to see here that's taking place, that on the interval from negative infinity to a, our function is increasing. However, the derivative of the function on any point on that interval is going to be positive. And again, we can start viewing this as well for any part of the function that will be increasing. Notice the function starts increasing again once we get to this latter portion of this interval for this function. It will be increasing once again. As such, in other words, that the slope of that derivative, or the slope of the function, will be positive. Anytime that occurs, we get that the function is increasing. So again, here we get a positive value, which means that my function overall is increasing. Oops. There we are. Now, what happens when we have a negative slope? Well, when we have a negative slope, that means that my function is decreasing. And we then want to identify on what intervals is my function decreasing. All right, so that's definitely one other item that we want to observe. And I'll go here. We still have a negative slope. Negative slope. And we still have a very steep negative slope here. And so from here, you're going to see that my derivative for these intervals that we're looking at here, from a all the way to e, that derivative is going to be negative. Anytime that our derivative turns out to be negative for any value evaluated within the interval, then that means that our function is going to be decreasing. Notice the top line here on the axis that I'm writing. The top line represents the derivative for the function. The bottom line represents the actual function and the description of what is taking place for that function. And so just by analyzing these two items, we then get to establish what is taking place within this specific graph. So one of the things that we then want to outline is we then want to outline on what intervals is the function increasing. Okay, so in order to analyze this, then we're going to say that the function f of x is increasing. And remember, increasing implies that the derivative of the function is greater than 0 on the interval, or on the intervals, from negative infinity to a, union from e to infinity. So these are the intervals that my function is increasing on. Now we want to see decreasing. Okay, so now we want to see where f of x is decreasing. So f of x is decreasing, meaning that the derivative of the function is going to be less than 0 on the intervals, and we have the intervals from a to c. So from a to c is our first interval here, so a to c. Union from c to e is where we're going to keep on decreasing. There we are. Now, again, the reason we want to analyze this is because oftentimes we might want to make an interpretation of a function without actually looking at a graphical representation of that function. And we want to solely rely on these algebraic extractions that we're looking at when we're talking about this function. If we look at the derivative, and if the derivative is positive for an interval, then the function must be increasing. If the derivative is negative, then the function must be decreasing on that said interval. And more specifically, we want to identify this particular piece of information that we want to extract where a maximum or where a minimum is going to occur for a function. Now, a maximum or a minimum can occur so long as it is relative or if it's absolute. And in order to extract that maximum or minimum, we then want to identify by the first derivative, is the function increasing and then decreasing after a certain point, or was the function decreasing and then increasing? In that sense, it will be extracting a specific maximum or minimum value for the function. But we'll get to that in a little bit. Now, aside from this, I also want to look at the second derivative. Now, for the second derivative, this one's going to be a little bit more tricky, but for the second derivative, if we get that the second derivative is negative, what will that imply for the function? Well, a derivative being negative will imply that your function is opening downward. We call this concavity. Concavity implies that your function is opening downward if it's concave down. Concave up is going to imply that the function is opening upward. As you can see on this graph, I have concave, the graph is concave down on the interval from negative infinity to b. So we say here that this function is concave down. Now, again, that only occurs if the second derivative is negative. This function is also concave down on this interval, meaning it's opening downward from c to d. So on the interval from c to d, we get that the value is negative for the second derivative, which again implies that we are concave down. And we're also going to have one more option. This one last option is going to be where my function is concave up. If the function is concave up, then that means the second derivative is going to be positive. And what does that mean then? Well, if the second derivative is positive, then our concavity for the function is concave up. Now, let's extract this into a little bit more of a proper setting. We're then going to write this as f of x is concave down, meaning that the second derivative is going to be less than 0, meaning it's negative. And this is going to be on the interval, or on the intervals for this case. Concave down, we got it from negative infinity to b, union from c to d. And we also have that the function f of x is concave up whenever the second derivative for the function is greater than 0, meaning that it needs to be positive. And this is only going to occur on the intervals from b to c that we've identified, union from d to infinity. And again, this only holds for the graph that we're observing here. Now, typically, when we go through the process of extracting these critical values or these critical numbers will then get an extraction for us that we're looking for when we're looking at the values for A, B, C, D, or E. It's only when we go through and we test them using the first derivative or the second derivative that we actually get to find out whether those points are going to be maximum or minimum values, or whether they're going to be called inflection points. These inflection points that we're discussing here are the points where the concavity switches direction. So if we can identify the first point at which my function changes concavity is going to be at this point that I'm outlining on the screen here. That point is b comma f of b. Another point where this function changes concavity is at c comma f of c. And the last point where the function changes concavity, that one's going to be d f of d. And so these 3 points are known as inflection points. And inflection points tell us where the function switches concavity, where it switches from being concave down to concave up, or concave up to concave down. So let's write this up. The points b, f of b, c, f of c, and d, f of d are called inflection points. And again, these inflection points are where the graph switches concavity. Okay, so why is it important to know this? Well, we're going to see then here from this particular graph that if we use the first derivative, where the first derivative switches from a positive to a negative sign, or where a derivative switches from negative to positive, we're either going to have a maximum or a minimum value depending on what sign switches. If the critical value that we extracted is of the same sign on both directions, meaning to the left of C it's negative and to the right of C it's negative, then nothing is occurring there, at least for our sake when we're talking about maximum or minimum values. Second derivative tells us about concavity. If our function is opening downward, then that must mean that we're going to attain some sort of maximum. If the function is opening upward, then that has a possible value that we can extract where it might be where it might be a minimum value. It's only when we go through and when we check that we want to identify what is actually happening. Okay, so in this particular instance, what we want to identify as well, when we're looking for these particular values, A, C, or E, what we're doing is we're taking our derivative and we're setting it equal to 0. Again, we're finding where these slopes are going to be horizontal. And that's where these are occurring. In other words, these are critical numbers. So it's going to be important for us to identify that. And not only do we want to identify that, but we also want to extract that a function could also be undefined. The derivative of a function could be undefined, and that in itself would also produce a critical number. So we don't want to limit ourselves to just be zeros. We want to find all critical numbers where the function could be undefined. Now for the second piece, where the second derivative is equal to 0, then we're going to find these values. And so again, we now get to establish this pattern where we get to find these maximums or these minimums. And this now leads us into what is known as the first and the second derivative test. The first and the second derivative tests are based off of the values that we were looking at here for this particular graph. This tells us that, or let's go with the first derivative. The first derivative test tells us that suppose that C is a critical number of a continuous function, f. If the derivative changes from positive to negative at the value of C, then the function has a local maximum at the value C. Number 2, if the derivative changes from negative to positive at C, then the function has a local minimum at C. And part C, or number 3, if the derivative is positive to the left and the right of C, or if it's negative to the left and negative to the right of C, then the function has no local maximum or minimum at C. Second derivative test. Second derivative test then tells us that we're going to suppose that f is a continuous function. So if f is a continuous function if the second derivative is a continuous function near C, then we're going to have part A. If the derivative at C is equal to 0, meaning we found that critical number, and we test that critical number on the second derivative, and the value is positive, then f is going to have a local minimum, because again, we have concavity upward. So if it's concave up at that given value, then we know we're going to have a local minimum. Same thing happens for part B. If the second derivative evaluated at C gets a 0, meaning we found a critical number, and the second derivative evaluated at C is less than 0, meaning it's negative, that's concave down, then the function has a local maximum at the value C. And we also have one more item. Part C. If you found that critical number, and when you're using the second derivative test, if the second derivative test produces 0 or produces that the value does not exist, then the second derivative test fails. Then the test is inconclusive. And we're going to have to then use the first derivative test in order to extract what is that value. So I'm going to say, so use the first derivative test. And when we use the first derivative test, we're going to be able to extract what is that value. Okay, so we're going to go through and we're going to now start analyzing by using the first and the second derivative test to extract what it is that these values are going to produce. All right, and so what we want to do here is we want to use this example where we're going to use the first derivative test to find the local minimum and maximum values of this given function. So one of the first things that I'm going to notice here, or I'm going to note here, is I'm going to note that x cannot be equal to 1. And the reason for this is that x cannot be equal to 1 because it will make that denominator 0. And we want to avoid those values. In other words, x is equal to 1 is not in the domain for this function. So we want to keep that in mind. Furthermore, we can actually say that we have an asymptote at x is equal to 1. So here we would have an asymptote or vertical asymptote at x is equal to 1. All right, so we want to keep that in mind. Now, we're going to go through, and in order to use the first derivative test, we're going to have to make sure that we take the derivative of the function. Okay, so we're going to go through and we're going to find that derivative of the function. So we're going to take the derivative here. And the derivative of this function is going to imply that we need to use the quotient rule. The quotient rule is going to say that we need to take the derivative of the top. So that the derivative of the top is going to be 2x oops, sorry about that. There we go. So the derivative of the top is 2x multiplied by x minus 1 minus x squared multiplied by the derivative of the bottom, which is just 1, divided by the denominator squared. This derivative will now simplify. Numerator turns out to be 2x squared minus 2x and then minus x squared divided by x minus 1 quantity squared. And then we can simplify this just a little bit more. This will then get us x squared minus 2x all divided by x minus 1 squared. Perfect. And so what we're going to do now is we're going to find these critical numbers. That way we can go through the whole process of identifying where we're going to have these maximum or minimum values occurring. Now, one of the items that we want to observe here first is that we also have this asymptote that we're going to worry about. And this asymptote is still going to happen when that denominator is equal to 1. So what I only need to worry about in this particular case is when my numerator is equal to 0. Therefore, I'm going to be able to extract when this derivative is equal to 0. So the derivative is equal to 0 when my numerator, x squared minus 2x, is equal to 0. This then implies that x times x minus 2 will be equal to 0, which then gets us that x is equal to 0 or x is equal to 2. So the values that we get, these critical values that we're observing, is going to be when x is equal to 0 and when x is equal to 2. And remember, we still have a vertical asymptote at x is equal to 1. So we're going to need to account for that. So let's go through and let's use that first derivative test. In order to use the first derivative test, what we're going to do is we're going to draw an interval. All right, here's my interval. It goes from negative infinity to positive infinity. I know I have my critical numbers that I'm looking at, x is equal to 0, x is equal to 2. I also know that I have a vertical asymptote. So the first thing that I'm going to do is I'm going to start sketching, or I'm going to start identifying all of those values. So I have x is equal to 0. There we are, and again, these are all x values. X is equal to 1, and then x is equal to 2. Perfect. And so again, we have a vertical asymptote here. So that's your vertical asymptote. Okay, so here we have the critical numbers of 0 and 2, and we're going to identify now what's taking place by using the first derivative test. So in using the first derivative test, what we're going to need to identify is what is happening to the derivative of the function. So we want to look at f prime of x. So f prime of x, we want to identify that, and we then also want to identify what is happening to the overall function f of x. So I'm actually going to denote this with a different color. It's going to be f of x, there we are, f prime, and then f of x. So in order to find these values, what we're going to do is we're going to test one of the numbers in the first interval. And the first interval is going to be from negative infinity to 0. So we're going to go ahead and we're going to pick some random number in that interval. And simply because any number within that interval should produce the exact same sign for the derivative. Meaning if the derivative is going to be positive, then any number that we choose in this interval will make that derivative positive. And that's independent of whatever number we choose, again, in that interval. So if we choose, let's say, the value of -1, well, choosing the value of -1, we're going to make our substitution, and actually I want to choose this in a different color. There we are. So let's say I choose -1. Let's make the substitution of -1 into the function. So making the substitution of -1 into the function, into my derivative, f of -1, we're going to get -1 squared minus 2 times -1, all divided by -1 minus 1 squared, which we get 1 plus 2, all divided by 4. This turns out to be 3/4. Now, at the end of the day, we're not really too concerned with the actual number. We're more concerned about the sign on that number, meaning is the number positive or is the number negative? In this instance, you see that the number is positive, so my derivative here is going to be positive. Well, what does a positive derivative imply about my function? Well, that implies that the function is increasing. Okay, perfect. Let's go on to the second number. Well, we need to pick a number between 0 and 1. So picking a number between 0 and 1, we could go with -1/2. I think that would be a really nice number. So let's say we go with -1/2. Making that substitution into the derivative, or sorry, not -1/2, my apologies, just 1/2. We get 1/2 squared minus 2 times 1/2, all divided by 1/2 minus 1 squared. Here we're going to get 1/4 minus 1, all divided by, that's going to be -1/2. -1/2 squared is just 1/4. Multiply everything by 4, and we get 1 minus 4 over 1, which means we're going to get -3. Which means the interval from 0 to 1 is negative. Which means our function is decreasing. And we can keep doing this process for the rest of the intervals. Well, we now want to observe what's happening on the interval from 1 to 2. We can choose a midpoint of, let's say, 1.5. So what happens if we choose a midpoint of 1.5 and we substitute that value into the derivative? All right, making that substitution here, so that's going to get us 3/2 to the power of 2 minus 2 times 3/2, all divided by 3/2 minus 1 squared. Well, this is going to be 9/4 minus 3, all divided by, this is going to be 1/2. And so if this is 1/2, 1/2 squared is just 1/4. Multiply everything by 4. And so what we're going to have is 9 minus 12 over 1, which is -3. And again, we get this to be negative, which means the function overall is decreasing. And we need to choose one more value from 2 to infinity. You can choose any value you'd like. For simplicity, I'm just going to go with the value of 3. Make that substitution into the derivative. So we get 3 squared minus 2 times 3, all divided by 3 minus 1 squared. This is going to be 9 minus 6. 9 minus 6 is 3. 3 minus 1, that's 2 squared, that's going to be 4, which means we get positive 3/4. So this value in the derivative in the interval from 2 to infinity is positive, which means that the function is increasing. Now, what does this mean for us? Well, in the first derivative test says that anytime that we're taking the function, that our function is increasing and then it switches to decreasing at a certain point, then we're going to have a local maximum. So what's happening is that my function is increasing and then it's going to be decreasing, which means we have some sort of maximum occurring. From the interval from 1 to 2 and then from 2 to infinity, so from 1 to 2 the function is decreasing, and then from 2 to infinity it's increasing, which means we're going to have a local minimum. So we now see here that by that extraction we can have a local maximum and a local minimum. The thing is, now we want to identify what those values are. So in order to identify what those values are, we're going to need to substitute in the x values, those critical numbers that we identified. Substitute those values into the function. So I'm going to say here, substitute x is equal to 0 and x is equal to 2 into f of x to find the values of the maximums, or of the local max and local mins. All right, so let's check them out then. F of 0, well, that's going to be 0 squared divided by 0 minus 1, which means we get 0. F of 2, that's going to be 2 squared divided by 2 minus 1, which will then produce a value of 4. So now we get to summarize all this. F of x has a local maximum of, and let's see, local max occurred at x is equal to 0. X is equal to 0 produced a value of 0. So f of x has a local maximum of 0 and this is when x is equal to 0. And has a local minimum of, let's see, according to the first derivative, local minimum occurs when x is equal to 2, but that value of the minimum was 4. So it has a local minimum of 4 when x is equal to 2. Perfect. And this here, this labeling, is what I want to see. That is what I am looking for. So in order to identify what it is that I'm looking for this problem, if the instructions say that we must use a first derivative test, then you must show that you took a derivative, you analyzed when that derivative was either going to be undefined or when it's 0, identify those values using the intervals, and then I want to see some work being done for you to test those intervals. Once you extract those intervals and you've identified by the first derivative test where the function is increasing or decreasing, then we can go ahead and identify what those values are for the local maximums and the local minimums. Perfect. So let's go through and let's work on the second derivative. We're going to use a different example to illustrate the second derivative test. All right, so here's an example. We want to use the second derivative test to find the local minimum and maximum values for this function g of x. And so again, just identifying that we're going to have to find this second derivative, or we're going to use a second derivative test, is going to imply that we need a second derivative. And so that's where we start. We take a first derivative, and we're going to get 6x minus 6x squared. And then taking a second derivative is going to imply that we're going to get 6 minus 12x. Now, in order to use the second derivative test, we first need to identify what are the values for which the first derivative is equal to 0. So again, in order to use this, we then need to find, when g prime of x is equal to 0. So that's one of the first things that we do as well, is we're going to take g of x and we're going to set this equal to 0, which then implies that 6x minus 6x squared will be equal to 0. Factor out your 6x, and then you get 1 minus x to be equal to 0, where we now get that x is equal to 0 or x is equal to 1. As such. Perfect. So now we're going to go through the rest of the process, and we're going to start extracting, or we're going to start analyzing the second derivative. All right, so now that we have our values, we're going to go ahead and we're going to test them on our second derivative. And so when I'm going to test them in the second derivative, I'm just going to write here test the values using the second derivative. Great. So g double prime, I'm first going to test it at 0. So the second derivative evaluated at 0 then gets me 6. And this second derivative, again, I'm looking at the signs. This sign is positive, which means it's greater than 0. And if it's greater than 0, then this means that we have the function to be concave up. If it's concave up, then that means we're going to be looking at a local minimum at 0. So that's one of the items. Okay, so now I also want to look at the other value. So g double prime at 1. So this is going to be 6 minus 12 times 1, which is negative 6. And again, this derivative, second derivative evaluated at 1, is going to be less than 0, which means this is concave down. If it's concave down, then we have a local maximum. So now that we've extracted this, we're going to go ahead and we're going to find what are those values. So in order for us to find those values, the first thing that we're going to do is we're going to evaluate the function g at the value that we initially looked at, so g of 0. G of 0 is going to get us 36. Then we evaluate g of 1, so the value for the function value at 1, that's going to be 36 plus 3 minus 2, and that should be 35 as such. Oh, sorry, not 35. My apologies. Should be 37. There we are. So now we can then extract, and we can say that g of x has a local maximum. And again, when it's concave down, it's going to have a local maximum, and it's going to have a local maximum of 37 when x is equal to 1, and a local minimum of 36 when x is equal to 0. And again, this is by using the second derivative test. And so again, that's what we want to observe, that we are using this second derivative test in order to extract those values, whether they be minimums or whether they be maximums. Perfect. So this is the whole process that we are working with when we're looking for these maximums or minimums by using the first or the second derivative test. So I hope you all enjoyed the lesson, and I look forward to reconvening our lessons with the next one, where we're going to be looking at limits at infinity and horizontal asymptotes. Till then, I'll see you.